Here's an example of another improper integral, this time type 2. We have the integral from -1 to 3 of 1 over the square root of 3 minus x dx. At first glance, this looks like an ordinary definite integral. We have the integral of a function on an interval from one bound to another bound. This is perfectly normal. The problem comes if we think about what the behavior of this function is on the interval from 1 to 3. Let's draw a quick graph of the function and see what goes wrong. Let's look at the function f of x equals 1 over the square root of 3 minus x. If you graph this function, you'll find that actually over here when x is 3, if you try plugging in 3 into this function, we're going to have 1 over the square root of 3 minus 3, which is 1 over the square root of 0. Now, the square root of 0 is perfectly fine. The square root of 0 is a number. It is 0. But 1 over 0, that's a problem. This is undefined. In fact, this function actually has a vertical asymptote at x equals 3. And the function is going to look something more or less like this. It's going to go off to infinity as x approaches 3, and it will also approach the negative x-axis as x goes off to minus infinity. So over here is -1. And the area we're trying to find is the area inside here. Now we have the same problem that we had with our type 1 improper integrals, that the region whose area we want to find is unbounded. This region is bounded in the x direction. It goes from -1 to 3. But in the y direction, it keeps on going up and up and up forever. Now, that bit that's going up and up and up forever is getting thinner and thinner and thinner. So maybe it will turn out that we still have a finite area here. But we might not. It depends on exactly how quickly the function is approaching the asymptote x equals 3. So we don't know until we try and compute this integral. And furthermore, we simply don't have the tools to compute integrals for a function that is discontinuous on the closed interval that we're trying to integrate over. Remember, the fundamental theory of calculus requires that our function be defined and continuous on the interval from -1 to 3, or whatever the interval is that we're trying to solve, the closed interval in particular. It has to be defined all the way through. So what do we do if we have a function that is not defined at one of those endpoints? Well, we'll do the same kind of approach that we took for type 1 integrals. What we'll do is we'll just pick a variable here, another bound that is not quite as far as 3, and we'll just chop that up right here, and we'll find the area instead between -1 and t, this new variable t. Now this area is clearly not quite as big as it should be. It's less than the area we want, but it is a bounded region, so we can actually find this area. We'll find the integral from -1 to t of our function, 1 over the square root of 3 minus x dx. Now, that's going to be too small for the answer we're looking for. It's clearly less area than the area we're looking for. So what should we do? Let's just push that t closer to 3. Let our t be a little bit closer, and we'll still have a finite area, but it'll be a little bigger, a little closer to the area we're actually trying to find. In fact, we'll keep letting our t get closer and closer and closer to 3, and we'll keep seeing what our area is going to be and see what that's approaching, what that's tending towards. Let's take the limit as t approaches 3. Now, in particular, t is only going to approach 3 from below because we want to stay within the overall region whose area we're trying to find. So let's make sure we put a little minus after our t to tell us that we have a one-sided limit as t approaches 3 from below of the integral from -1 to t of our function. That's what we'll do to solve this problem. So let's go back and look at our problem. So we determined that because our function is discontinuous at 3, and in fact undefined at 3, that what we'll need to do is we need to convert that problematic endpoint, that problematic bound of our integral, to a variable. We'll call it t. Also, we'll go from -1 to t of 1 over the square root of 3 minus x dx. And then we'll just, as our second step, we'll take the limit as t approaches that 3 from below. So let's work this out. The first thing we'll want to do is compute the integral. And we'll just keep writing our limit expression here because we have not yet computed the limits. Limit as t approaches 3 from below of this integral. Now, how should we solve the integral? This is a very simple u substitution. We can actually do that u sub without writing it out as long as we are paying very careful attention to what we're doing. But since it's going to be a little bit tricky, let me write it out here. Let's write a u. Our u will be 3 minus x. And our du, therefore, is going to be negative dx. This is what makes it a little bit tricky here, because if you aren't quite paying attention, you might miss that negative there. I am not going to change my bounds because I think it's going to make things a little more complicated than I want to. So let's just have the integral from x equals -1 to x equals t of 1 over the square root of u. Now, I can write that as u to the -1/2. And then instead of dx, we'll want negative du. So perhaps I'll just put the negative in front here, negative du. And now this is an easy integral. We'll just solve this here. This is the limit as t approaches 3 from below of negative u to the +1/2, because we're going to raise the power by 1. We also have to divide by the new power, so divide by 1/2. But of course, that's the same as multiplying by 2. And we are going from x equals -1 to x equals t. And we'll just put our u back in, so we'll have this equals the limit as t goes to 3 from below of -2 square root, because u to the 1/2 is a square root of 3 minus x, going from -1 to t. So we'll just finish filling in our bounds and then solve this limit. Let's make a little more space here so we can work this out. So I've made a little space, and this is going to be equal to the limit as t goes to 3 from below of -2 square root of 3 minus t minus a negative, so that's +2 square root of 3 minus -1. Now, 3 minus -1, that's actually 4, and the square root of 4 is 2, so that's a 2 there. Just work this out here. And furthermore, as t approaches 3, from above or below, 3 minus t is going to be 0. The square root of 0 is 0. So we actually have -2 square root of 0 here, which is all going to go to 0, plus 2 times 2. So that's all 0. Again, don't be tempted to say that the square root of 0 is undefined or any of that. No, the square root of 0 is 0. It is a number. It is perfectly fine. This resulting antiderivative is actually defined everywhere on our function here. And we will have 2 times 2 gives us 4. And so our answer, our actual area, is 4. So that region that we looked at the graph of, even though the region itself is unbounded, it appears that that curve is approaching the asymptote quickly enough that that little sliver that goes off to infinity is narrow enough and is getting narrower enough that it still has a finite area, and that total area ends up being 4. Now, by the way, in this situation, if you had forgotten to treat this as an improper integral because you were not paying attention, and if you'd forgotten to note that your original function in your integrand was undefined at 3, you would have gone merrily along your way solving this integral and plugging in the bounds of -1 and 3, and you actually would have gotten the right answer. You would have gotten away with it. But there are going to be other situations where you don't get away with it. So you do need to pay attention, and from this point forward, make sure that you check and think about in every definite integral that you do. Think about, is my function defined everywhere in the interval over which I'm integrating, including at the endpoints. And if your function is undefined somewhere in that interval, then you'll need to treat this as an improper integral. Here's the general definition of how we should approach improper integrals. The first case is the case that we had in the example we just did. If your function is continuous on the half-open interval from a to b, in other words, it is continuous at a and never inside the interval, but discontinuous at b, you'll need to convert your upper bound, which is the problematic bound, into a variable, call it t, and then take the limit as t approaches that upper bound from below. In other words, we're going to just push that t, that arbitrary upper bound, closer and closer and closer to the real upper bound that you want, which is b, and you'll take a limit and see what's happening to that area as your upper bound gets closer and closer to the real goal of b. Maybe you'll end up with an infinite result. Maybe you'll end up with something finite. It will depend. If your function is continuous on the half-open interval from a to b, where it's continuous at b but discontinuous at a, the lower bound, same idea. You'll just convert that problematic lower bound a to a variable t, which is above a, and then you take the limit as t approaches that a from above. So t is higher than a, which is therefore giving you a smaller overall region. And then you'll push that t closer and closer and closer to a and see what's happening to your area. Take a limit. As long as that limit in either case is finite, in other words, a number that is finite, that's your answer. If that limit is infinite, either plus or minus infinity, or if it doesn't exist at all, which can happen sometimes, then we'll say that the integral diverges.